In this video, I will show you how to test for stationarity using unit root tests. In addition, I will show you how to handle non-stationary time series. In a previous video, we discussed stationarity and data generating processes. So if you missed these two concepts, go back and watch them now before you continue watching this video. We explored first-order autoregressive processes. On the slide you can see an AR1 process. We know that if a coefficient A is equal to 1, non-stationary behavior emerges. The AR1 process becomes a random walk. Note that the error term epsilon t is IID distributed, which means that it is identically independently distributed. Hence, the error term is a white noise process. Past realizations cannot predict future realizations. The error term is stationary. To test whether A is equal to 1, we have to modify the equation by taking minus yt minus 1 on both sides. This gives a first differenced equation. This is needed to avoid spurious regression results if the time series is indeed non-stationary. Now this equation is the cornerstone of the Dickey-Fuller test. We now look for this coefficient denoted gamma, and we test whether gamma is equal to 0, which implies that A is equal to 1, which in turn implies that the time series is a random walk, which means it has a unit root, which then means it is non-stationary. It's important to note that the Dickey-Fuller test uses the null hypothesis that the time series has a unit root. It is non-stationary. So if you cannot reject the null, it means that the time series is non-stationary. That's important to have in mind. We now move into Stata and look again at the Bitcoin time series. I opened a do file. I already navigated into the right folder using the change directory command, and then I opened the data set which we used in a previous video. This time I want to focus on closing prices. The first thing I always do is I have to declare my time series. So I use the tset command and then date var, so this is my date variable. Then it would be useful just to visualize the time series, doing a line chart on the closing price and the time dimension. It seems to drift away. Certainly it's hard to argue that it has a constant mean or any well-defined moments. But how can we now formally test that? As we just discussed, we use a Dickey-Fuller test. In Stata, this is implemented in the command dfuller, and then we specify the name of the time series. And we obtain a test statistic, and the idea is now to compare this test statistic to critical values. Now this is a so-called one-sided test. Again, if you want me to discuss this in more detail, just leave a comment below. The interesting thing is just to look at the p-value. Obviously this p-value is quite high. It's 0.61. We know that it should be below 0.05 to reject the null at the 95% level of confidence. This p-value suggests that we cannot reject the null, which means the time series is non-stationary. Now what to do about it? There are different ways to handle it, and we explore alternatives in later sessions when we talk about cointegration. But number one remedy is to take a first difference. Now when you look at the equation involved, if it is indeed a random walk, so if A is indeed 1, then taking a first difference would reduce it only to the white noise process, so it should fix the problem. Now, how do we do it in Stata? It's quite easy. We just use the d-dot operator, which we can use after the tset command. And obviously just doing the first differencing actually does the trick. You see now it's pretty much acknowledged that it goes back to a long-term equilibrium, which is somewhere very close to 0, which again is not a big surprise for financial time series. And then we have these clusters of high volatility, and we will go back into this volatility modeling much later in the course. The next thing you do is you rerun the Dickey-Fuller test on the first difference time series. Now we can clearly reject the null hypothesis. So that means after first differencing once, it is now stationary. You call this time series integrated of order 1, because after first differencing once, we obtain a stationary time series. So that's all for this video. We will of course explore these issues further. There's much more to discuss around stationarity, and I will leave it for other videos. I'll see you in the next one.